Hi, my name is Aaron Young. I'm a NASA postdoctoral fellow at NASA's Goddard Space Flight Center. I'm here to share with you the excitement I have for both NASA's flagship instruments, the James Webb Space Telescope and the Nancy Grace Roman Space Telescope. I will talk about how theory can help steer future observations, and I'll show you some of the simulations that I created in anticipation for their science. You see, the coming decade is an exciting time for studying galaxies and how they evolve with the universe. First, JWST will be able to go much deeper in space, and it will deliver answers for the many things we want to know about the earliest epoch of star and galaxy formation. Then we will have Roman, which will give us a much wider panoramic view of the cosmos. With a field of view 100 times bigger than that of Hubble's, we will find so many more galaxies and quasars, and we will be able to have a rather comprehensive look at the extremely large cosmic web structure. So first, let's start by revisiting this gorgeous image in the background. This is the Hubble Ultra Deep Field taken in 2004 with the Hubble Space Telescope, with exposure time just less than 1 million seconds or 400 orbits. Approximately 10,000 galaxies show up in a small patch of seemingly dark sky, and we learn an incredible amount about our universe from this image alone. It contains galaxies that were forming all the way back within the first billion years after the Big Bang. By looking at galaxies identified at different times throughout cosmic history, we are able to put together a fairly consistent physical model to explain how galaxies formed and evolved over time. Here I show you a simulated version of the Hubble Ultra Deep Field made using the Santa Cruz Semi-anlaytic model, or SAM. SAM is a powerful tool for creating this sort of simulations because they are both driven by physics and they are computationally efficient, meaning that they only require a small amount of computing time. We can process millions of halos overnight on a laptop, significantly cheaper than a hydrodynamic simulation. And yet, the SAM is made up of key physical processes that are involved in galaxy formation that were derived from past observations and other simulations. It can efficiently produce physically backed predictions for a large population of galaxies. Just like the one I show on the right-hand side, every data point represents a galaxy, and these data points are size-coded and color-coded by their rest frame UV luminosity. So bigger and darker data points represent galaxies that are brighter and more massive. At this point, our model is fairly successful at reproducing what we see in the real universe, including galaxies' physical properties like their mass and size, and also their luminosity and color. And taking advantage of such a physical model, we can now also make predictions for galaxies that we have not yet seen, but are expected to be seen with JWST. Here I've added another simulated field that includes the additional faint galaxies that JWST is expected to see. And I just want to enlarge a small portion of the simulated field to help us visualize how many more galaxies are expected. I'm calling this work Semi-anlaytic Forecast for JWST, in which we provide all sorts of predictions for high redshift galaxies that are expected to be detected with JWST. And with a simulation like this, we can also interact with the dataset in many interesting ways. On the left, I'm rotating a dataset show you the distribution of galaxies in 3D space. This is what we often refer to as a light cone. It is a great visualization for how the observed galaxies are physically distributed in space. At the end, I mark a handful of redshift just to give you a sense of how that compares to physical distances. So now let's put these light cones to work. Here is an example from my work with the Cosmic Evolution Early Release Science Team, or CEERS, which uses one of my simulated EGS fields in their survey planning. In observations, we constantly ask ourselves, how deep do we need to go, or how much exposure time is needed? And in return, how many objects do we expect? And with JWST's parallel capabilities, it is just super important to get these pointings just right so we can get the most science out of our allocated time. Simulated light currents in this case makes a very useful playground for conducting experiments and even help developing other mock data products, mock images, and the data reduction pipeline itself. So now let's take a break from JWST and go back to the Hubble Ultra Deep Field. In this tiny patch of the sky, there are about 10,000 galaxies, and the field is a little less than 6 square arc minutes in the sky. But how big is it actually? Let's put this into perspective. Here is the ultra deep field next to the moon for scale. And now you see our universe is really full of galaxies, but we are not quite able to see them all if we can only survey the sky at this rate. But if we keep an eye on that red Hubble Ultra Deep Field box, it will be there for the next few slides to guide the scale. So here is the next big thing, really, really big, the Roman Space Telescope. I have a single pointing of Roman highlighted in green here. We also put the Andromeda Galaxy behind it for scale. Roman's field of view is enormous. It is about 100 times bigger than Hubble's, and it is going to see the universe at similar depth as Hubble as well. Let's take a moment to appreciate how much quicker can Roman survey the universe. I just added the candles fields to scale for comparison. These are the largest fields visited by Hubble so far. In the past, I've created light cones to help us better understand and interpret what Hubble has observed. I've also increased their mass resolution so that they contain galaxies that only JWST can detect. But for a wide field instrument like Roman, what we currently have is clearly not enough. We need to be able to capture more of the large-scale structure, the cosmic filaments, the voids. We can't just stitch a bunch of smaller fields together. We need to get realistic statistics for the universe. So I went on and created these 2 square degrees simulated field, a single field that is bigger than all the other ones combined, with self-consistent predictions for spatial distribution and clustering of galaxies. A field that is predicted with sufficient physics that you can trust and do science with. And I didn't make one, I made a total of 5, 2 square degrees each, which adds up to 10 square degrees of sky, and that is 72,000 square arc minutes in total. Over 60 million simulated galaxies in total. All of these cones span the range between redshift 0 and 10, containing galaxies as low mass as 10 to the 7th solar mass. This is an enormous simulated data set for us to play with while we wait for Roman to take off. And you can get your hands on the data today. We're going to release the JWST and Roman cones you saw in the next month or so. But we do have light cones for candle survey that are already public. The new data set will be in the exact same format. So if you really want to, you can already start looking at them and start developing code that works with the data set. And here, let me show you a quick demo. To gain access to the data, simply go to the Flatiron Institute's Flat Hub. You can just Google that. And from there, select Santa Cruz SAM or SC SAM. And then you're in. This is an interactive portal that allows you to make simple plots, sub-selected data, and even allows you to download only the data you need, so you don't have to download the full catalog, which sometimes can be pretty big. And for example, here, let's set X and Y to RA and DEC, and have the color reflect the magnitude of the galaxies. And we're done. We have plotted the EGS field. So thank you for listening, and stay tuned for the upcoming simulated data releases, and get excited for NASA's upcoming flagship space telescopes.